Hi, this is the next video which talks about the sources and consequences of having error in your model. So here are the sources of error, and Beamer does a very nice job of breaking this out in the case of surveys. Obviously, some of the errors are not going to be applicable to administrative data, that is sampling error and non-response error, because you have data on all the people who are being administered by the government program. We talked a little bit about coverage error. I'm going to spend a bit of time here talking about measurement error and data processing error. And of course, I'm not going to talk so much about the model error. We'll talk about that in the next presentation. But essentially, it's trying to just write down all the components of the error that we talked about in that flow chart that we had in the previous video. So unpacking this in terms of measurement error and processing error, you could think about that as the difference between the measure that the data are collecting and the measure after it's been edited. So I'm going to drill down into this one because it's quite an important one, and I'm going to talk about data processing error as well. So I think the best way to think about this is in terms of an actual example. And so the example that I wanted to talk through is the situation where you have a very rich data set, scanner data. So let me talk about this in the context of the problem that's trying to be solved. So the problem is you want to try and figure out whether people are eating healthy food. That is an important policy goal. Unhealthy diets lead to early death, to obesity, all kinds of medical problems. And of course, it's very hard to figure out what people eat from a survey. It's very difficult to get their responses accurate. People forget. It's very expensive to capture that information. So scanner data, which is generated from the scans when you go in and you purchase something at a retail or a grocery store. So essentially what it does, when you think about this, the receipt that you get, the scanner information captures the price and the quantity of every single thing that you purchased. So scientists at the US Department of Agriculture try and take a look at that to understand at least the purchases of food by Americans. This captures information from about 60,000 supermarket and grocery chains throughout the country. So I'm just going to give you a little flavor of this terrific work that's been done by researchers. And so here's the problem. They want to figure out the healthfulness of food purchases. Now, as we all know, purchases and actual eating are very different things. A lot of food gets wasted, but at least this captures some of the information. So when you have information about the goods that are purchased, you've got information, see on the left-hand side, about what is contained in those purchases. So this is the observed data. Now what you want to do is you want to try and translate that into something that captures the nutritional value. And this isn't just something that they're doing because they think it's interesting, well, of course it is, but it's also mandated. The Secretary of Agriculture is required to publish the market baskets of the Thrifty Food Plan. And so essentially that's going to be used to determine what subsidies are going to be provided for food stamps, for feeding hungry children. There are a lot of families who are food insecure in the United States. So it's very important policy implications. Now, here's the challenge that the scientists face. So the scanner data captures information in a variety of different ways. You have loose products like a pomegranate, a bunch of carrots, peas, And what they need to be able to do is they need to be able to take the information on the left-hand side. There might be 450,000 different ways in which goods are made available in the store, and they need to translate that into the edited version of that is maps onto the measure that they're really trying to get at, which is the measure of healthy food. So you can see when you get overwhelmed by massive amounts of data, what you're really trying to do there is you're trying to take the observed information and turn it into something that can be analyzed. And so human beings and anyone is going to have, there's going to be some error in that translation. Sometimes errors come about simply because the data are bad. So we have this classic situation where when we teach data science, and I was on this National Academies panel, you know, you kind of assume that you have this perfect data set all nicely and neatly in rows and columns. And if the data are in there, it's going to be good. But very often, and this is an example from a class that we ran using corrections data, and you can see here in Slack, someone is, and I've deleted their names obviously, and they're asking what on earth is going on here from the administrative data. The actual results don't make any sense. And the CIO of this Department of Corrections, who was in the class, said, yeah, it's bad data, just ignore it. So you actually need to have some understanding of how the data are generated and get a sense of the measurement error as a result. So how can you reduce measurement error? Well, there are a number of different ways. First of all, consider the source. I've kind of talked about this a lot, but understand the data generating mechanism. So just because it's administrative data doesn't mean that it's necessarily good data. I'm going to give a couple of examples. For example, when you deal with data, say, coming out of an administrative system, just because it's there doesn't mean that it exactly represents what you think it represents. The example I'm going to give is when I was at the National Science Foundation, we were asked to identify immediately when we were processing grants, we were asked to categorize them by whether they were basic or applied. And so obviously it's almost impossible to think through what basic or applied means when you're a program officer reading different grants. So pretty much the default was 80-20, 80% basic, 20% applied. So every single grant would have that 80-20 ratio. Then about when I had been at NSF for about 3 years, we were told, oh, NSF only does basic research. So we changed, everything was 100%. So automatically, just as a result of administrative issues, the administrative value of basic versus applied research changed dramatically. So think about the source. In general, data that have to do with the core function of the agency that it is administering the program is going to be pretty high quality. So if, for example, with unemployment insurance wage records, you need the social security number in order to administer the program, or you need the name in order to administer the program, it's going to be pretty good because those errors are going to show up very quickly. If they're not needed to administer the program and it's just something that someone's told you to do, it's going to be pretty bad. So keep an eye out as to how it's generated. One way of thinking about how to reduce measurement error, try and get different sources of the same measure to see if it makes sense, if the summary information makes sense. A related thing is to get outsiders to take a look at what's going in, evaluate it, and if it's going to be important, and give you feedback. In my experience, probably the best way to get high quality data is, instead of focusing in on the inputs, is to focus on the outputs. So take a look at the summary statistics, have people use it for programmatic purposes, And if the results are really weird, the people who are using it will say, that doesn't make any sense. So kind of instead of obsessing about getting high quality input all the time, take a look at the outputs, provide them back to the people who are using it to administer the program, and pretty soon you'll get a virtuous loop that continuously will improve the data because it's getting used. Data that aren't used, no one's going to care about, and it's kind of a waste of time anyway. So related to that is thinking about the data processing error framework. So Paul Beamer does a very nice job of this in your textbook. So I've spent a bit of time talking about the way in which the data are generated. Are they generated from sources that are high quality? How are they extracted and transformed? That was what I was talking about with the food quality example. How is it loaded and stored? Then kind of how do you pull the data out? How are they filtered? What subsets of data are you taking and then doing the analysis? So that's kind of the whole process by which things work. And there can be a lot of errors associated with this. So data could be missing. There could be selection in the units, or you may simply not have any data documentation at all. So for example, a classic situation will be in administrative data, the categories will change and there won't be any documentation telling you that the categories have changed. So what can happen is a category will go from 6 categories to 4 categories, and you have no idea why or how it's been collapsed. You have to find someone to tell you how that category changed. Even more perniciously, I've been in a situation in which the a measure like gender, which is often coded as 0-1, will get coded as 1-2, 1 for male and 2 for female, and people don't pick up on that. And so that flip in the data coding can cause really different results. So pay attention in every year when you've got longitudinal data to find out what's going on. The missingness can occur, and I'm going to talk about that in just a minute. The missingness can occur particularly in longitudinal data where you track the same observation over time. So you might have someone show up in one year, not in the next year, and then again in the subsequent year. So trying to understand why those patterns are missing can be really important as well. And I'm going to give you an example of that too. So missing data are probably the most pernicious problem. Well, there are a lot of problems with working with any kind of data. So they can be obviously data that are missing completely at random, just that for whatever reason, some row or some individuals just don't show up in the data. That's not so very common. Obviously, if it's missing at random, it's not a bias problem, but it can reduce the power of the data. The more pernicious problem is when the data are missing at random. So the challenge here might be when you're collecting the data, the data are missing systematically for different groups of people. So for example, if I'm dealing with, let's say, collecting data on for the decennial census, and a particular group of individuals who aren't citizens systematically don't respond. So the challenge here is that if I don't adjust for that non-response, I am going to run into problems with a bias because those subgroups are not going to be adequately captured. Now, if it's systematically different as a result of ethnicity or race, I can attempt to model that because I know that it's different for different subgroups and I can just weight it up. I'll talk about that in just a minute. But missing at random, conditional on observed data, means that within the data set, I can do some adjustments. A bigger problem comes up when it's missing not at random. So in other words, there's some systematic measure out there that I don't know, which means that the data are missing, and I don't really know what's causing it. So that can bias our results. A good summary is provided in this journal article. If it's missing completely at random, then it's just random chance, and it doesn't systematically bias it other than reduce the power of our statistical test. And so one way in which people address that is just delete the stuff that's missing, the pieces that are missing. That can cause, and that's called list-wise deletion. I'll talk about that a bit more in a minute as well. If it's missing at random, if it's because of demographic characteristics and so on, there are ways of modeling that out. You can use, in particular, multiple imputation is a very common way of addressing it. If it's missing not at random, then you've got to try and figure out what's going on, and that can be quite hard to do and beyond the scope of this discussion. So the consequences, as I have said, it reduces power, introduces bias. The worst thing you can do is to ignore it. So let me give a concrete example. Suppose I'm interested in looking at the earnings and employment outcomes of people who are educated within a given state. And so I look at the I look at education records, I link those education records to the wage records in a state, and I say, oh my goodness, here's the return to investment in a state of people taking different degrees. And so what I see is the earnings and employment outcomes of computer scientists or data scientists, and I compare those to earnings and employment outcomes of, let's say, nurses. Now, the challenge with that is that, and I ignore missing values. If I don't get a match in earnings and employment outcomes matched to state earnings and employment records, I just ignore it and run the regression, even though maybe 30% of the people don't show up in the first year after graduation. Well, the bias that might result there is that the people who are missing from computer science may have gone to California or to Texas or to New York. So and they moved because there are higher earnings there. So my estimate of the return to investment in computer science is going to be too low. The same thing might be true for nurses. If I see that I graduate a bunch of nurses and this is their earnings and employment outcomes in that particular state, again, it might be that there are higher earnings in a contiguous state and you're completely missing those individuals systematically because the ones who could make more money went to another state. So that's going to downwardly bias the estimate of the returns to earnings, to that education. And even if there isn't a bias, the increase in noise when you have measurement error at best reduces the precision of your estimates and downwardly biases it. So there are lots of ways of handling this, a lot beyond the scope of this particular video. The weighting mechanism tries to re-weight the importance of the data that you have and by controlling for the relative selection of people in a particular cohort. Imputation just takes the missing values and replaces them with a model-based estimate. And then maximum likelihood tries to model what is the reason for these rows to be missing, and then just fits it in as part of the analysis. So here are some questions for you to work through, and look forward to getting your responses in class.